Okay, so today we're going to look at a couple of things that arise out of thinking about the conservation of momentum and how they relate to forces. And we've got to start by saying there must be some relationship, because if you apply a force to something, you will make it speed up. And if you make something speed up, then that is going to change its momentum. Now, the first thing that I want you to do, if you haven't already, is to just watch the video of the slow motion football kick. For no other reason, it gives us a kind of idea of what collisions are like in reality as opposed to a kind of idealized version. So in the video, you will have seen that when you strike a football, there is a time at which the foot is in contact with the ball. So you will have a foot, in a football kick, there will be a force that's applied for a time, for a certain time, which causes acceleration and hence a change in momentum. So what I want to try and do is, because we've got the force, which is our starting thing, and the change in momentum, which is our ending thing, I'm just going to see if I can sort of skip, and find out a relationship which is directly linking my force to my change in momentum for this object. So I went and I researched some information about football kicks. So a football strike can lead to a ball which is stationary. Okay, so we're going to deal with a football. That ball is stationary. It's got a initial speed of 0 meters per second, and it's got a mass of mass of a football is about 0.4 kilograms, so 400 grams. That's the mass of the ball, and we apply a force to it. That force, the foot touches the ball for a time. So time of force of 0.02 seconds. So a really tiny amount of time. So, and afterwards, so this is sort of like before, and this is what we get afterwards. Our ball has shot off from the person's foot, and it's moving in that direction. How fast does the ball, when you strike it, move? Well, it's now going at a speed of 30 meters per second, and it still has the same mass of 0.4 kilograms. And I would say, right, I want to know what the force is. I'm interested in what force is applied to that ball to make that situation. Well, if we think about Newton's second law, that tells us that force equals mass times acceleration. And acceleration is v minus u over t, the change in velocity over the time it's taken to achieve that change. So what we get is the acceleration is equal to v, which is 30, minus u, which is 0, over the time taken, which is 0.02. And if we do that, 30 minus 0 over 2, we get 1,500 meters per second squared. That's the acceleration of the ball. So the force equals mass times acceleration. So that is 0.4 times 1500, and we get 600 newtons. So we apply a force of 600 newtons for a time of 0.02 seconds. We get a change in the speed of the ball that's going to end up, they're going to get an acceleration which is going to give us a change. Ultimately, that ball's going to move at 30 meters per second away from us. And that's kind of a Newton 2 approach. But what I'm actually going to think about it now is, well, can I link this force to how the momentum of the ball has changed? So let's think about this in the terms of what is the... so we can do a momentum approach. Well, we can think about our original situation. Originally we've got u equals 0, m equals 0.4, that's meters per second, that's kilograms. So our initial momentum is equal to 0 kilogram meters per second. And then afterwards, we've gone to here, where we're moving at v equals 30 meters per second, m equals 0.4 kilograms. So our momentum, which is the final, is equal to 30 times 0.4, and we've got 12 kilogram meters per second. Now, that change from situation 1, before the ball was kicked, to situation 2, after the ball was kicked, the time between those two situations is 0.02 seconds. Now, this gives us another way of thinking about the problem. What is it if we do the change in momentum over the time taken to achieve that? Well, we do 12 kilogram meters per second over 0.02, and we get 600 newtons, which is the same as we got by doing F equals ma. So there's another way in which, if you're dealing with momentum, there is another way of calculating force. The force that has been applied to, you can work out the force that's been applied to a subject is the change in momentum divided by the time it's taken for that change to take place. So this leads to something here. So we get this, the force applied to an object to change its momentum is the change of momentum over the time taken. Now, you might feel that this is just another way of writing the same thing, but it allows us to put forces in terms of the time it takes for that force to arise, because there is something that this makes clear that F equals ma doesn't quite. If you're going to bring something to a stop, then you want that time to be as big as possible, because the longer it takes for a change in momentum to occur, the smaller the force you need to apply. That is the difference between a light touch on some brakes and hard braking in an emergency stop. It is the difference between falling onto the ground directly or falling while you're wearing knee pads. Okay, loads of safety features are designed to increase the time it takes to come to a stop. Okay, so to minimize forces when bringing something to a stop, we want to maximize the time taken. Now, where does that occur? Well, it's often in a case where there's been some form of accident or some kind of fall, but in many cases, something like a car. So a car when a car collides with something, if you are in a passenger seat, so you're driving a car, and you collide with something that is quite immovable, such as a wall, well, that collision, if you had a car made entirely out of steel that is not going to compress or buckle, well, that collision is very sudden. You hit it and you stop. And so that time is very small, in which case you are going to experience a very large force in stopping in such a short amount of time. If, however, you think about a modern car, which has loads of safety features, such as airbags, seat belts, there are things called crumple zones. So the front of the car isn't designed to just sort of, hit the edge and stop. It's designed to kind of crumple inwards, so it kind of breaks apart and you end up with what can look like a really dramatic crash, but the car's designed to do that. You might even see cars that are designed like, where the wheels will come off and fall away because it's designed to carry some momentum away in order to make it so that collision happens over as much a period of time as possible. A second example that you can see is something that you'll see if you go sort of to any kind of sort of play parks. What you'll find on the ground isn't just concrete. There's one of two sort of options that you tend to see in this. Either you see stuff like, that sort of wooden barky stuff that's everywhere. So it's all kind of loose and stuff that's kind of like got a lot of give into it. So it's got a kind of like crumply zone on top of it. So rather than it being onto concrete, you can fall on it. And that extra time it takes to come to a stop means that's the difference between, just a small bump and being in quite a lot of pain. Or they've got that other weird stuff that they use, which is the sort of the dark kind of cushiony sort of material. So it's got a little sort of bounce to it. And they seem small, it seems subtle. But what it means is that if you sort of are playing on the swings and you do what everyone does when they play on the swings, they go, oh, you know what I'm going to do? I'm going to go wee and go wee. When you land, what will happen is not an instantaneous stop. You will land on something that will deform under you, take a little bit of extra time for you to come to a stop, and it will mean that you are able to do that with less forces. There are things that you do in this collision as well. You bend your knees, you might roll, you will do whatever you can to not stop in an instant. So there is a huge thing about the fact that this relationship is what tells us that by increasing the time it takes in a collision for you to stop, the smaller the forces that you are exerted to. And given that in many collisions the time is so small, anything you can do to extend it tends to have a really big gain. if you double the time it takes to stop, you have halved the force that you will experience. And that is the difference between, in terms of getting out of certain things with much lesser injuries than you would otherwise have. So that is a kind of example, and we'll look at a bit of an example on that in a moment. So at this point, here's a quick question that goes through this. Feel free to pause the video, have a look at it yourself, and then you can see how well you do. But let's go through this. It's going to use that rate of change. So complete the following sentence. The momentum of a moving object has a magnitude in kilogram meters per second and a direction because it is a vector. Then we've got a car being driven at 9 meters per second collides with the back of a stationary lorry. The car slows down and stops in 0.2 seconds. The total mass of the car and driver is 1,200 kilograms. Calculate the average force exerted by the lorry on the car during the collision. Show clearly how you work out your answer. Well, the idea is that it's going to stop. Okay, so the final momentum is 0. Okay, so we've got the average force is equal to change in momentum over time. The change in momentum is all the momentum. It initially would have had 9 times 1,200. So that equals 9 times 1,200 over 0.2. So I'm using the wrong end of my pen because it's run out of battery, so that's always upsetting. 9 times 1,200 over 0.2, and we get 54,000 newtons. A lot of newtons. Part C. Within 0.04 seconds of the car hitting the back of the lorry, the car driver's airbag inflates. The airbag deflates when it's hit by the driver's head. Use the idea of momentum to explain why the airbag reduces the risk of the driver sustaining a serious injury. So what we have in this one is, that's a very quick time, but essentially we are going to increase the time it takes to stop. That's the first thing that's going to happen, which therefore decreases the rate of change of the momentum. So which therefore reduces the force. You can sort of say that in other ways. You can say that you can say things like that. You can make a direct reference to the equation and say that by increasing t or like decreasing the rate of the force, you can make sort of versions. But basically, 3 points that go along this kind of thing. I look at the mark scheme now, and it says except increases the time taken to reduce momentum to 0 is worth 2 of the 3 marks. And then the third mark is for saying reduces the force. So that's that video. Don't do the next question because that's for later on. The second outcome from thinking about momentum, it uncovers something called Newton's third law. If we consider this kind of thing with a crash, okay, we know that because the car is the thing that's sort of like driving towards the wall, well, that car is going to crash into the wall, so it's going to be pushing on the wall. But we also know that the car stops, the car decelerates, so that must also mean that the car itself, there is a force on the car as a consequence of striking the wall. And that happens in any form of collision. Okay. And one of the things that Isaac Newton realised is that all forces come in pairs. So every action has an equal and opposite reaction. Now, basically all forces come in pairs whenever there's a collision, and this is something of a sort of like it's a bit of a strange sort of thing to consider, because on the surface it sounds like nothing should happen if every action has an equal and opposite reaction. Well, that must mean every force must cancel out, and so nothing occurs. But this is important because they are acting on different objects. Examples of Newton's third law would be something like if you've got the Earth and you've got a person standing on the Earth. Well, the Earth pulls down on the person with their weight. Let's say it's 500 newtons, a 50 kilogram person. Newton's third law says that that person is actually also going to pull up on the Earth, again with a force of 500 newtons. Now, the Earth is much, much, much bigger than a person. The mass of the Earth is incredibly huge. So you don't notice that 500 newtons. It's just not big enough to do anything. But that's what this is what a Newton's force pair is. So, the force of the Earth on the person is equal and opposite to the force of the person on the Earth. But the white force is acting on the person, the blue force is acting on the Earth. Another similar example tends to happen, and they seem to like these ones when people are on ice skates of some description. So got people on ice skates. I should really probably have these two people like that. So I've given that person a third arm. Let's get rid of that. And let's have these two people sort of on ice skates. So this thing. Okay. In a scenario like this, so let's say you've got Alice and Zoe. Well, this case here is that if Alice, which I'm going to get rid, if Alice pushes on Zoe, so Zoe just stands there, doesn't feel like they're doing anything. But if Alice pushes Zoe, and let's say pushes her with a force of 100 newtons, there will be a reaction force from Zoe on Alice, which is also 100 newtons. And this is why when two people on ice skates, if they push against each other, they will both accelerate, they both drift apart, they both move in opposite directions. Alice is going to move that way, Zoe is going to move that way. Now that's what Newton's third law is. As a weird extension, we can see actually how it arises from Newton's laws of motion, so that we can deal with a collision. So let's deal with a collision. So let's say we've got an object, Alice, another ball, let's call it ball Z, and let's say that this object is moving in this direction with a speed of 10 meters per second, and let's say it has a mass of 5 kilograms. Let's say the second object has a mass of 2 kilograms, and let's say it is not moving. Let's deal with the stationary impact. And let's say that therefore we can say the momentum of this object is 5 times 10, so we've got 50 kilogram meters per second. The momentum of this object is 0. And let's say that afterwards, so this ball is sent off let's say 8 meters per second, and we can say m equals 2 kilograms. So we can get the momentum of that thing is 2 times 8, which is 16 kilogram meters per second, and then that must mean that this object must have a momentum of 50 minus 16, 34. So this object must have the rest of the momentum, which is 34. It's got a mass of 5, and so therefore it would be moving that way at 6.8 meters per second. So that's solving a problem using a conservation momentum. Okay. Well, let's say that there's a time of the collision, because there must have been a time, when these two things collided, they had a time that they were together. And let's say that the time of the collision let's say that is equal to 0.1 seconds. So they come together, there's a collision as they interact for 0.1 of a second as they strike, and then they carry on moving. Well, we've seen how we can work out the forces on these things. Okay, we know that force is equal to change in momentum over time. So we can say, okay, what's the force that was on deal with Zoe? I keep calling this ball Zoe. I don't know why. I've just gone with Z. So these two people have run into each other, which is a bit awkward. So the change in momentum. Well, the initial momentum is 0. The final momentum is 16. So we've got 16 minus 0 over 0.1. So we've got a force of 160 newtons. 16 minus 0 over 0.1. What is the force acting on Alice? Well, Alice finishes with a momentum of 34, starts with a momentum of 50, and this is important because the change in momentum therefore is final minus initial. So 34 minus 50 over 0.1, and that equals minus 160 newtons. Same force, same size force, but opposite direction because one of them has a negative sign. So the conservation of momentum leads to this thing called Newton's third law. And in fact, actually, Newton thought about it the other way around. He started with Newton's third law and ended up with the conservation of momentum. But it was a subtle law. Sounds like he's being greedy with having 3 laws, but this is the third law. Whenever you push against one object, that object will push against you with an equal and opposite force. And as with other things, we're just going to work through a little exam question example for you to see. Okay, final question. I'm going to look through again. If you want to give it a go ahead of time, feel free, or if you just want to follow along and see, okay, how was this problem solved? So we've got an ice skater throwing a 0.23 kilogram snowball, certain velocity. So we've got a state and equation linking momentum, mass and velocity. Momentum equals mass times velocity. Calculate the initial momentum of the snowball. I'm guessing that means the initial once she's thrown it, not initial as in when it was in her hand, is my guess. Yes, because otherwise there wouldn't be really anything there. So we've got a mass, got a velocity, 0.23 times 13, and we get 2.99 kilogram meters per second. Then we have when the skater when the skater throws the ball forwards, she slides backwards on the ice. Explain why she moves in this direction. Now, because they're very similar, there are two ways of solving this problem. But the way we're going to think about it is, how do we do this with Newton's third law? So, well, if you mention, there is a. Oh, well, that's not nice. That's my. So if we mention the concept of there being an equal and opposite reaction, okay, means that there's, due to forces on skater and snowball, so you are linking the two forces that are going to be there. Okay, so equal and opposite reaction, forces on skater and snowball, and so I think that they get. So you will get. She will, therefore, have a change in momentum backwards. Sorry, it's pretty hard. That's terrible handwriting. It's really difficult writing with this end of the pen. So this is the idea. If you get any mention of Newton's third law, an equal and opposite reaction, so any mention of Newton's third law gets you a mark. Talking about equal and opposite, you get another mark. Saying that there'll therefore be forces on both will be this gives you the third mark, which is really all you're looking for. But if you say therefore that you get the change, the rate change and the change of momentum is the same for both, you'll get the final mark. So if you do make a final link towards momentum, you get the final one. You can, however, answer that question entirely possibly without even mentioning Newton's third law. You can do that with with the sort of like conservation of momentum. So you can say momentum is conserved. So therefore, you will get momentum of snowball and skater are equal and opposite. Okay, so because initial momentum is 0. So it's not saying you won't find huge sets of questions that are all about Newton's third law. It just gives you another way of answering sort of this kind of question. Why does one move forward and one move backwards? Then we have a situation which is very similar to the previous one. The skater wears soft knee pads that compress easily. Explain how that protects her knees when she falls on the ice. So if you fall, you have things that you will do is that you increase time of the impact. However, you have the same change in momentum, because whether you fall over with or without knee pads is going to have the same sort of like change in momentum. So you can make a link to force is equal to change in momentum over time, and therefore you have a F decreases. And that's sort of the 4 points that they say. You can, as I was looking at the mark scheme, you can actually say you can go at this in other ways. You can go at a way of you can just do it in terms of acceleration, and you can say, well, you will increase the time of the impact, which decreases the acceleration, which will reduce the force, so you can attack it like that. Or even you can say, well, a knee pad has an increased area, so you reduce your force because pressure is force over area. It's not what they were expecting you to go with, but enough people did to make it a way into this that people were, happy to give marks for. And so that's the other way of doing this kind of problem.